changed a little bit since I realized that Chibo is going to be here also talking about alkaline atoms. So then it was a good opportunity for me to focus on a given only one topic, that is polar molecules. Although you will see during my talk that there is a very strong connection between what I'm going to talk and what Chibo is going to talk in his, well, later today. All right. So also let me emphasize that this work is in very close collaboration with the experimental group. It's a just combination of theory and experiment. And therefore, I'm going to start by thanking my collaborators. There is a very nice and fantastic theory team of postdocs, graduate students, and Misha even, that he is here. And of course, in very close collaboration with the experimental KRB team, Junji and Debbie Jean are the group leaders, and a fantastic group of postdocs and graduate students, and of course, thanking the funding agencies for support. All right, so let me start my talk with a quick outline. So I'm going to start with a motivation. I'm going to tell you why we think ultra-cold polar molecules are ideal for simulating quantum magnetism. And then I'm going to tell you a little bit about the observation of exchange interactions that we have just recently done at Jila, and some new ideas about how to simulate a spin-orbit dipolar exchange in polar molecules, more or less connecting what Victor said, but in a new type of systems. And finalize with an outlook. So I want to start this talk with a very interesting idea of Phil Anderson. He was Nobel Prize in 1977, who said more is different. And the idea is that, well, even though if we are able to understand the behavior of few particles, that's not necessary enough to understand the behavior of macroscopic system. And certainly the understanding of macroscopic system is one of the hearts of modern quantum science. And the idea, or why this complication is related with the fact that, well, quantum mechanics of a many-body system is complicated, and we have to face and we have to deal with quantum complexity, quantum correlations, and quantum entanglement. And all these three words, or these phenomena, it makes this connection very hard to establish, although we know that certainly we want to understand many-body behavior because it has very interesting macroscopic phenomena that could have very important technological applications. So we want to do that. And the question is how we are going to accomplish this, given that these are the heart of modern quantum science. And for that, there was a proposal of, well, can we use ultra-cold atoms in order to accomplish that task? And, well, certainly ultra-cold matter has unique capabilities because it's fully controllable. And the capabilities that we can, or the capability of ultra-cold matter is kind of, or it's very well reflected in that using ultra-cold matter, we are building the most precise measurement devices. And I can measure, for example, quantum sensors and clocks, and more about the clocks and the excellent precision that clocks are achieving is going to be, Chibo is going to tell us about that. So the idea is that besides this tremendous capability, we can use ultra-cold matter for understanding quantum complexity. And well, in that respect, then I remind you a very provocative idea by Richard Feynman, that is quantum simulation. Can we use a fully controllable quantum system to understand the behavior of a more complicated system? And well, certainly this could be a very interesting idea, and building a quantum simulator that allows us to understand the behavior of the complicated materials is going to be very interesting. So we want to use atoms in an optical lattice, or molecules, I will mention, to simulate the behavior of electrons in a solid-state crystal. So certainly this is something very appealing, and this is something that is becoming a common effort on the field. However, there are challenges. And what are the challenges? Well, we are not dealing with actual electrons, but we are dealing with atoms. So atoms are certainly much more heavier than electrons. And well, the optical lattice spacing is optical is micrometers, whereas typical ionic lattice spacing of order of angstroms. So these two very different in energy scales imposes a strong limitations on the temperatures that we need to achieve in order to mimic the desired behavior in solid-state systems. So if we want to mimic the behavior of phenomena that happens in solid-state materials at Kelvin temperatures, that translates to temperatures that are about picokelvin or a few picokelvin in our atomic systems. So certainly this is really challenging, but doesn't mean that it's impossible. And certainly there has been very important developments, for example, on cooling techniques. Here at Harvard, for example, Marcus Grider has been able to create a microscope that he can assemble initially the atoms to reduce the entropy at very low and a corresponding of very low temperature, but it still is kind of limited. So the question is, for example, we could explore new type of systems. So maybe one of the big limitations of this one-to-one correspondence is the fact that we are thinking of the simplest atoms, one outer electron atoms that only interact with contact interactions. Maybe other systems that have richer internal structure and more complicated interactions could relax the required limitation of the temperature scales for seeing same phenomena that we expect to see in atoms at very low temperatures. So among the systems that we are trying to explore right away, or the communities try to explore, is, for example, polar molecules, alkaline atoms that have two outer electrons, not one, trapped ions, magnetic atoms, Rydberg atoms. All of them have a much complicated internal structure, but this complicated internal structure may allow more knobs in order to understand more complex behavior. And that's the goal, and this is, I'm going to tell you that certainly this is the case. And at Jila, we are focusing in these two systems, polar molecules and alkaline atoms. We see these are, we have been inspired by clocks on how to probe interaction in polar molecules, you will see. But also let me tell you that the techniques that we are using here can be used equally, are equally applicable in order to model and understand the behavior of other type of more generic systems. All right, so why polar molecules? What is new with them? Well, certainly they have new internal degrees of freedom. They have vibration, they have rotation that you don't have in cold atoms. Second, you can explore chemistry with them. So certainly the possibility of using those molecules for exploring ultra-cold chemistry is something that is new. And in addition, they have a strong and long range anisotropic dipolar interactions. And this is something new that we don't have with atoms. So this is really appealing. But then there is the complication. So if you think about what the development of the field, in 1995, it was the first observation of a Bose-Einstein condensate, where we can reach temperature of hundreds of nanokelvins and densities of 10 to the 13 centimeter per cube. However, if you then see what happens almost more than 10 years after that, and you look at what was the evolution with polar molecules, still we were stuck with 100 microkelvin and densities of only of 10 to the 6 per centimeter cube. And the reason is why. Or the question is why, and the reason is molecules are very complex. So if you want to cool down molecules, you have to deal or expand control energy scales that span more than 10 orders of magnitude. So you not only need to control the binding energy, that is thousands of Kelvin, you need to control vibrations, you need to control rotations, you need to control the hyperfine and cool them down such that they can be trapped in like atoms. So this is a really big challenge. And even though it's complicated, it was actually achieved at Jila in 2008. So in 2008, the Jila group reported the realization of an ultra-cold or almost quantum degenerate gas of polar molecules. So what they did is they start with a gas of fermionic ultra-cold potassium atoms, fermionic atoms, and an ultra-cold gas of bosonic atoms, rubidium atoms, BEC, and they were able to combine them and with them create almost quantum degenerated gas of polar molecules in the raw vibrational ground state. And these molecules do have a large dipole moment, or well, compared with atoms. That, so the dipole-dipole interactions that Dan was talking about, for example, here, these are much more bigger. They have a 0-point divide. So you can see, if you think what they have achieved, they were able to create a system that is 10 times colder and approximately 1 million times more dense than the prior results with ultra-cold molecules. So that sounds a fantastic possibility. It was a great achievement. And just briefly tell you how they did that. They did that by using controlling interactions, what is called a Feshbach resonance, and combining this these gases in very weakly bound molecules that have almost zero dipole moment, but then transferring these weakly bound dipole molecules into ground state molecules using a stirrup. So that means light is the key. Light was the key. Light was the photons were what carry the energy, and using the photons, they were able to really bridge these 10 order of magnitude energy scales and create molecules in the raw vibration ground state. So certainly that was a fantastic achievement, opened a big window for exploration, but then there was a problem. After this achievement, then they realized that these molecules, even in the ground state, they were very unstable. They decayed through chemical reactions. And the lifetime of this gas in 3 dimensions was just millisecond lifetime. This is certainly not enough for understanding the physics that we wanted to understand with them. Well, but certainly there is not a very limiting problem. We always create a solution, and the solution was immediately proposed by theorists, by Peter Soller, John Bond, where they said, well, maybe if you can confine the molecules in very tight one-dimensional lattice, then you can avoid these bad collisions and take advantage of the dipole moment. So basically the idea is that molecules that approach together in this tightly confined 2D geometry, when the molecules approach in this direction, they repel to each other, so they don't decay. And this direction that was when the molecules attract and was responsible for the decay was suppressed by the confinement. So using these 2D traps, or 1D lattice, and creating these tightly confined pancakes, actually they were able to extend the lifetime of the molecules from milliseconds to seconds lifetime. So this sounds very promising now. But that's not enough. So this is at the time when I arrived at Jila, and then we load the molecules, or they load the molecules in the lattice, and then we provide theoretical feedback and say, well, you should get force repression in the lattice. And certainly that was the case. So this is the lifetime of the molecules, but the total intensity of the light used to trap them. And you can see that when you start with a 2D lattice that creates an array of tubes, then in this case the lifetime is the same as in the pancakes, approximately 1 second. It's not a big deal. But then as soon as they add a rugosity along the tubes, you see, whoop, the lifetime was boosted, and now they can reach lifetime of the order of 25 seconds. That's a big difference. And the idea is very simple to understand, is that because these molecules are fermionic molecules, and as soon as they load them in an optical lattice, 2 fermions cannot be in the same state. So 2 fermions cannot be in the lowest band of the lattice. Therefore, these collisions, this Fermi exclusion principle, the Pauli exclusion principle, the quantum statistics is what it produces the blockade mechanism to avoid the decay. So that attributes the very fast increase in the lifetime. Of course, then there is light scattering, and we cannot confine the molecules with very strong. The light scattering is going to limit the lifetime, and that's what we see when we go to very, very deep lattice. But at least at this point, we still have molecules almost in a zero gas of molecules that are localized at the different lattice sites. And at this, in this case, we have a lifetime that can be as large as 25 seconds. And well, we are not quantum degenerated still. So this molecule is still, the filling fraction is dilute. We are only dealing with molecules with filling fraction of 0.1, 10%. So it's still very dilute. We are not quantum degenerated. But as soon as we saw these fantastic results, then theorists, we got very excited, and we made a prediction. The prediction was we should be able to see quantum magnetism even at these current conditions. Not quantum degenerate, it's still much more higher than that, but the molecules are localized and live forever. And why? Well, we were based on a model this is a paper that we wrote in 2011 with Alexei Gorshkov, that the key is that maybe, or what we can try to do is use the rotational levels of the molecule to simulate the spin degrees of freedom. That's the key. Why? Because these rotational states are coupled by dipole-dipole interactions, and therefore the dipole-dipole interaction could mimic the spin-spin interaction that we need to magnetism. The key advantage is that these dipole-dipole interactions are not mediated by the motion of atoms that happens for atoms. For atoms, the spin-spin interactions are mediated by hopping, and not only the energy scales are much stronger than that, but we are decoupling the motional and the spin degrees of freedom. That's a key. So we have strong dipole-dipole interactions. In addition, these dipole interactions are fully tunable with electromagnetic fields and microwaves. They are long range and anisotropic, so give a lot of flexibility. And therefore, and the key part is that, as I said, they are not mediated by motion. They can happen even in frozen molecules. And therefore, the spin is not, the spin temperature is not, is meaningless. So only if we prepare the molecules in a very well initial spin state, then we are almost having a pure state. So we don't need to worry about temperature. And that's the key. So motional temperature doesn't necessarily matter, and the spin temperature can be we can reach very pure states by initial state preparation. So, and with that, and the very very big difference between dipole-dipole interactions and the lifetime of the molecules, we should be able to see something. All right. So that was our prediction. So let me explain a little bit more how we can create a spin Hamiltonian from the dipole-dipole interactions. And the key idea is that, well, for our molecules like KRB, the internal degrees of freedom can be, the rotational levels behave like a rigid rotor. So you have these angular momentum type states with n equal to 0, the ground state, and then n equal to 1 that has 3 degenerated states in the absence of electric field, and this energy separation of the order of gigahertz. Okay, so now we apply an electric field, and what happens is that we can split these levels. So the molecules acquire a net dipole moment, and therefore this energy manifold is split, and we can isolate 2 of these degenerate degrees of freedom. We can isolate only 2 that energetically resolve, and we can use these 2 states as effective spin 1/2 model. So that's going to be our effective spin 1/2 model. So let me mention that there were other schemes proposed before, for example, using the hyperfine states of the molecule, but these were not ideal for our molecules because they are not coupling directly. They are perturbatively coupled. So in our case, we are using the rotational states that are directly coupled by the dipole-dipole interactions and give us stronger interactions. So certainly, well, that was the proposal, and well, it's not as ideal. Well, it's not like a pure as we thought. We have still the hyperfine interactions that couple the rotational states. So these states are not completely what the pure
Maria, this is for heteronuclear.
Yes. So KRB, we are talking about KRB. So in this case, the KRB, you don't have a pure rotational structure because hyperfine has we have still the quadruple interactions, but we can nevertheless in this KRB, this is specific for KRB, isolate 2 states as an effective spin 1/2 degrees of freedom. 2, they have some small admixture of nuclear spins, but they are more or less rotational levels. So we have these 2 as an effective spin 1/2 degree of freedom, and let's project the dipole-dipole Hamiltonian that is just 1 minus 3 cos squared, this d squared times, and this is weighted by 1 minus 3 cos squared r cubed. So molecules in this direction repel, molecules in this direction attract. This is this term here, and we can project this Hamiltonian into the 2 spin 1/2 levels that we use. And when we project this Hamiltonian there, assuming that the molecules are frozen, so no motional degrees of freedom, the next Hamiltonian that we get is a spin Hamiltonian. So the spin Hamiltonians tell me that depending if I have up or down, they just have different energy. This is the first term here, that the coupling constant, of course, depends on the dipole moment between the molecules. So in this case, these terms is only non-zero when you have an electric field where the molecules acquire a net dipole moment, but we have also the flip-flop terms where the molecules flip-flop between the states. So this is the flip-flop terms, and this can happen even in the absence of electric field because this term is just proportional to the transition dipole matrix element that is non-zero in 2 states that have different parity. So even in the absence of electric field, we can have these dipole-dipole interactions, flip-flop interactions. All right, so the question is how we are going to probe these dipolar interactions in our system. And this is where we were inspired by the clocks, where we say, well, maybe we can use similar techniques that people use in the clock to probe interactions. And this is the idea. So in clocks, you usually use Ramsey spectroscopy. In Ramsey spectroscopy, what you do is that you have the 2 spin 1/2 levels, you create a superposition between the two with the first poles. Then you let it evolve for some time. So this is just rotating your Bloch vector. This is a single particle. You let it evolve for some time. It requires a phase. For example, if you have a magnetic field in the rotating frame, just have a Bloch vector that rotates, and then you measure this phase that accumulates by the atoms, by the second pulse, that transfers coherence to population. That's what is done in the clock, and the two observables that you have is just the phase, that is give you your the frequency of your Ramsey fringes, and you have your the amplitude of your Ramsey fringes that will return the contrast, that tells you the coherence of your system. Basically, this is the two aspects that you measure in the clock. So this is one way to look at Ramsey spectroscopy. But if we talk with condensed matter people, there is another way to look at Ramsey spectroscopy. That is just a quench. So that means after the pulse, where you're preparing the state as if you have a Hamiltonian that has a very large magnetic field, that's it. So the molecules are going to align in the direction of the magnetic field, and this depends on the pulse area that you apply. Then you turn off the magnetic field, let the molecules evolve, that's the quench, and then you measure. So you can see that in two different perspectives, in the clock language or on the quench language. All right. So what we expect to see in when you have many molecules. So far, what I've just described is just the behavior of a single atom. Well, with many molecules, in principle, we'll say instead of one, we have n molecules, and therefore, in principle, instead of spin 1/2, you can define a collective spin. So just a macroscopic rotation of your spin, and this is what, in principle, you do with Ramsey spectroscopy. And if the molecules were not interacting, you were just going to expect all in sync, and you just have a big signal, and in principle, that's the idea for the clocks. But however, this is not necessarily what happens in the presence of interactions, because interactions make the dynamics very correlated, and you don't expect the characteristic evolution of just independent atoms. So the question is what we are going to see, what is the manifestation of these correlations when we deal with the molecules? That's the question. And well, we characterize, as I said, the behavior in terms of a phase and an amplitude, the contrast and the phase. So the contrast and the phase. And the phase can be understood as an effective magnetic field that other molecules create on a given molecule, more like a mean field effect. So I'm surrounded by many molecules. I feel the presence of the molecules as an effective magnetic field, and then this creates an additional precession, but it depends on interactions, and this depends also on my tipping angle of the pulse. If you have theta equal to pi half, you don't see an effect at the mean field level. So no mean field dynamics at theta equal to pi half. However, this is not the only effect. If you look at the length of your Bloch vector, like the amplitude, this is the amplitude of the Ramsey fringe, you can see that because of quantum effects, the length of the Bloch vector can decay and depolarize. And this depolarization can be proportional to sine theta. So it's maximum at pi half. Note that I'm not telling you that there is a decoherence necessary. So even if the S squared term can be conserved. So you might still be in the decay manifold. But interaction correlations that give rise to a squeezing are the type of interaction that can make your Bloch vector decrease. All right, so this is what you expect in principle to see, some type of dynamics in the amplitude and not in the phase. Then we have to deal with the filling fraction. So I told you the molecules were dilute. Only 10% of the molecules, the filling fraction is at most 10%. So how this affect the measurements? Well, actually it doesn't slow down the dynamics. It just introduces some defects, and you just have to do a disordered average of the different configurations in order to deal with that. That's it. So when we did simulations in a 1D system, what we found is that, well, these are two different tipping angles. One is pi half and the other pi divided by 10. And you do look at the contrast or the expectation value of Sx during the dark time. You see that, this is some dynamics that we can expect to see the decay of the contrast at times of order of milliseconds. That's certainly visible. And when you have a low filling fraction, so you see the different time scales here, the dynamics does not slow down, but only sees oscillations. And these oscillations come from the fact that the molecules only see pairs of molecules that are close by. So that's the main dynamics, is not the overall. So here is just a many-body effect with all of them experienced all-to-all. Here, when you are dilute, you mainly see the dynamics of your pairs next to you, and that's what gives you oscillation. It's more like cluster of 2, 3, or 4 particles. All right, so that's part of our prediction. So let's see what the experiments see. So that's something that is great at Jila, that you propose something and they do try to see if you can see.
What does the oscillation frequency mean?
Is J-perp, is the dipole-dipole strength between nearest neighbor molecules. So the dipole-dipole interaction goes like 1 over r cubed. So in the case, it's not only nearest neighbor, but you have the spin Hamiltonian, and just is the dipole coupling to the next nearest neighbor molecule.
Right, so from not reading the oscillation frequency there, you read the dipole coupling.
Exactly. So in the experiments, they did the experiment in a 3D lattice, and they could not use an electric field. The quantization axes were determined by the magnetic field, and well, now they are trying to deal with so one of the perspectives of the experiment is trying to deal with an electric field, but at the moment there is only B field, and they choose the orientation of the B field because they wanted to have a magic lattice for the 2 rotational states to avoid any other decoherence effects. So you can see this is your question. So here is the dipole-dipole strength that is completely anisotropic. So if I have a molecule here, I will see something that is negative between my nearest neighbor on top, but the nearest neighbor along the xy plane is going to be very different. For example, this is -1, this is 0.5, and either next nearest neighbor are going to have different strength and different sign. So the system can be quite anisotropic. In addition, they can control the strength of this dipole exchange by actually populating 2 different spin 1/2 systems. For example, if the spin 1/2 are between the 0, 0 and the 1 - 1, then in this case the molecules are almost rotating, and the time average of them gives you a factor of -1/2. On the other hand, if they populate the molecules 0, 0 and 1, 0, there is not a factor of -1/2, there is not the time average, and you can make the interactions twice stronger. All right, so this is what they did. So they did an additional pi pulse to account for any external decoherence and external dephasing that is not single particle dephasing, mainly coming from the fact that they were even close to magic but not magic in the lattice. So yes, so you see that they saw the oscillations that we were predicting because they were dilute, but in addition they see that the decay of the contrast decayed as a function of time, and the decay of the contrast was depending of the number of molecules. So they see that the oscillations are according to the nearest neighbor coupling constant that we were expecting from the neighbors along the z direction, and when they increase, they change the rotational state. You can see at twice this frequency, and they see the contrast, the coherence time actually went like 1 over n. So it depends on the number of molecules that we're expecting. So it's a really interaction effect. And then there was also dependence of the rotational states. So these lines were drawn just to guide the eyes. So in addition, in order to determine whether or not these interactions were really coming from dipolar effects, they adopted these NMR techniques to apply pulses. And in general, you can apply a sequence that removes the dipole-dipole interactions. So if in the case of they don't apply any pulse in the middle, you see very fast decay because of the no magic trap. When you apply the echo pulse, you see that the oscillations that I just told you, and when apply this type of NMR echo pulse technique, they see that the oscillations decay. So certainly we're giving some indication that what we're expecting were really coming from dipole-dipole interactions. But I think this was not convincing enough. So the question is, are those experiments really seeing dipole-dipole interaction in the decay? Is really determined by a XY model? And this was a question generally for the theories. But it's a very complicated system to deal with. So the interactions are strong. The system is not equilibrium, disorder because it's dilute. We are dealing with long-range interactions. We have to deal with 10 to the 4 molecules, and mean field predictions just don't work. So in principle, it's a very, very complicated system to deal with. Well, but we did manage to look at the dynamics. And what we did is a generalized cluster expansion. So in semiconductors, what they use is that if you have a system that is dilute, maybe let's divide in optimized clusters, just small systems. Each cluster you can exactly diagonalize. So you solve the dynamics within a cluster and you just assume that intercluster they do not interact. That's one way to capture the dynamics. This doesn't work for our systems. What we did is an improved cluster expansion that is called moving average cluster expansion, where you optimize the cluster for each atom. So you have your system, and now let's create for each atom the optimal cluster. So you look at this atom here, and then you create a cluster. For example, G is the maximum number of atoms that you use for the cluster. Then you look at this other atom, you create a cluster. The other atom, you create the optimal cluster. For each atom, then you compute XXI using this optimized cluster, and you sum over clusters. And well, we didn't know this method was going to converge, but so we can test it in some specific cases. For example, we use the dynamics, well, this is how you construct the system, and we use this cluster expansion for the icing case where we can exactly solve and we can determine whether our method was converging or not. So the standard, you can see that the standard cluster expansion, this is the exact solution, the solid line, the dots. And you see that the standard cluster expansion do not converge very well. It captures the behavior, but not exactly, whereas the maze very quickly converges to the exact solution. For the SY model, we did the exact calculations, but we don't have an exact solution. In principle, we see similar behavior. The oscillations are a little bit more stronger, but we don't have an exact solution to compare with solution with. But we do have experiment. So that's what we did. So these are the comparisons between our maze and the experiment. We only have one fitting parameter to determine the density, and then everything remains the same. So here we are seeing the dynamics for when they use 1 minus 1 and when we use 1, 0. And in this case, you can see the oscillations are twice faster here and here. Our solution actually agrees very well. So you can see here that if I rescale the time by a factor of 2, the two solutions that were different by a coupling constant of order 2, they collapse into each other, and the theory very nice predicts the observation. So I would say that this is kind of the case where theory helps the experiment to improve, and the experiment is telling us, helping us to improve the theory. So I would say that this is one of the first examples in polar molecules of a quantum simulation. We really didn't know the answer until we compared with the experiment, and now we have the theory, we can help the experiment to proceed further. So I see that Tony is standing up, so maybe how much time I have?
Well, 6 minutes for including questions.
Okay, so we're going to jump very fast onto that. So I'm just connecting what Victor was mentioning. So dipole-dipole interactions are not necessarily what I just mentioned. There are more diverse, so there is broader. So what I told you is the 1 minus 3 cos squared theta. That is one specific term of the dipole interactions. These are the terms that conserve the angular momentum. So if you have two molecules, they are the flip-flop terms that I was mentioning. But there are other type of terms that actually include changes in the, these are other terms that actually import changes on the rotational by a factor of 2. But that means my molecules need to acquire some angular momentum in order to compensate to the change in the spin degrees of freedom. So these are the terms here when, so these are the terms when I go from -1 to 0 to 1 and 0. So you are saying that you are transferring 2 units of angular momentum, but as a consequence, your molecules have to rotate. So this is a way to generate a spin-orbit coupling in your system. And it's exactly what people are talking about, the Heisenberg effect, that you need to conserve the total angular momentum, not only the spin or the motional degrees of freedom. It's the sum of both, and this has been actually used in magnetic dipoles. But we are proposing to engineer this in actually molecules where you can. So in this case, when you hop, if you look at a single molecule, a single excitation, that means when you hop, you have to acquire an angular momentum. So this is exactly a spin orbit Hamiltonian. And well, just briefly, so when you look at the excitation, you have a very phase that you accumulate that is 4 pi. So certainly it's a very non-trivial system where you can really engineer spin orbit coupling, and you can see here in the angular momentum. And just to finish, maybe just for fun, I can give you, for example, what we expect to observe if we create the molecules, we create an excitation in a spin up, mean the n equal to 1 state, and then you start to look at the other state, the other spin down, you can see that the system is acquiring a very phase, acquiring some rotation. So certainly this is a very interesting system to actually implement a spin-orbit coupling inherent from the dipole-dipole interactions. So yes, so the dynamics could be very interesting. You need to resolve it spatially, but still you can see this accumulation of phase in your molecules. So yeah, so I know that I went very fast in this last part. So, but I think the message is that in principle you can acquire orbital angular momentum from the dipole-dipole interactions, and actually this orbital angular momentum survive disorder. So you can see still that the phase is preserved when even for a dual system. So for that, let me conclude that polar molecules offer a unique laboratory for the exploration of many body physics. Losses are not only a limitation, and well, this is something that we have a PRL on this. Well, so I think we have proposed the first quantum simulation in action, and we have more rich physics to explore, that is a spin orbital dipolar exchange, and in principle we can also see the motion of the molecules into play, and we can explore itinerant ferromagnetism. So there are very rich systems that we can explore. Thank you so much.
Thanks for the talk. Any questions?
I have a question about this experimental plot which you fitted with the theory. So is there some thermalization going on, or is quantum pure quantum dynamics there?
Well, the system is equilibrating, is relaxing to zero in that respect. So the contrast, so if you look at these observables, well, first you can see clearly here that this observable is relating to zero, the expectation value of x is going to zero, and also that's what we have seen so far, and similar behavior is going in the experiment. So we don't have very long times that I'm showing, but this observable is relaxing to zero. The question is whether the correlation, you can see some thermalization in the correlation functions, and so far it's not that easy because in the experiment there is an additional source of decoherence that dominates the dynamic after long times. So that's why the comparisons we only show until these 40 milliseconds. After 40 milliseconds, the experiment, there is some additional source of decoherence that is going to dominate the physics. So whether we can control this type of decoherence and see thermalization, that's certainly one interesting question to add.
From the theory point of view, if you ignore experiments, look into your methods that you developed, how do you see how the system equilibrates to the finite temperature?
So far, the observables that we have seen decay all to zero. So the SX correlation goes to zero, and the other correlations are going to zero in general. So the question if there is signature in other type of observables, we have not seen, but certainly this is something interesting to look at in other type of observables that don't decay to zero as a function of time.